In this lesson, we will begin by talking about energy as an introduction to subsequent teaching sessions we will have. We will discuss briefly about the history of energy, and then we'll talk about several other details about energy. And all of these will be useful for us when we begin to talk about the core aspect of energy in subsequent lessons. So welcome on board and let's begin. Let's quickly look at the energy timeline. Over the years, there's been a lot of developments about the use of energy, and when we started using energy, when we started developing energy, when we started finding, recognizing the usefulness and how we can apply different types of energy sources to our daily lives. The first natural gas well was built or developed in 1821. The first oil well was developed and built in 1859, several years and decades ago. The first gasoline car was developed in 1892. The first power plant was developed in 1882, and it was used to send electricity to just 85 buildings. Until 150 years ago, the sun and wood provided most of the energy, and in many parts of the world, they still do today. The sun and wood are still providing as much energy as possible in several parts of the world today. Humans started using coal to power trains in 1850. We started using coal and oil to power energy plants in 1875 AD. Nuclear power was discovered by humans in 1930 AD. Humans started utilizing solar power in 1970 AD. The natural gas use became widespread in 1990 AD by humans. We cannot do without energy in today's world. Almost everything we do, right from our breathing to our sleeping, our waking up, to our eating and drinking, almost everything we do require energy. In our daily life, when you want to catch a ride home on a blustery winter day, you use energy. When you walk in the door and you relish the warmth of your cozy home, all of those are made possible because of energy. When you switch on the light or switch off the light, you are deploying the use of energy. When you go to the refrigerator, you are using energy. The refrigerator is using energy. You are also, using up energy. When you heat up a snack in the microwave, that is application of energy. When you cruise or browse or surf the internet, that is application of energy in another form. Okay, when you listen to music, when you make a phone call to a friend, when you flip on TV channels, when you take a hot shower, all of these are applications of energy up to the time that you go to bed in the night. So you find out that our daily life is actually made possible because of the use of energy. Without energy, there will be no life. For humans and all the other organisms, mammals and plants that we have in the world today. So without thinking about it, without planning it, without preconceiving the notion, you find out that you consume a lot of energy. You burn a lot of energy. By talking, by thinking, by laughing, by walking, you burn a lot of energy. Every day, about 13 kilograms of coal are burned to generate all the electrical energy one person uses. 13 kilograms of coal is required for one person. And that adds up to more than 5 tons of coal in a year. So when you look at the energy you use for transportation, you find out that in the US alone, an average citizen, an average resident in the US uses 1,892 liters of gasoline annually. So if one person uses that, imagine what 7 billion, 8 billion people on planet Earth would use. You are just one person with energy needs. Every human has energy needs, and you want to imagine how much energy every human, everybody, everyone in your classroom, everyone in your neighborhood, everyone in your office consumes. When you picture that, then picture exactly what the entire world population would need or would consume on a daily basis, on an annual basis, and on a going concern basis. Now, some questions you want to ask yourself, some things you want to bother about. Where does all the energy come from? Will there be enough energy to go around? Because the population is not static. The population keeps increasing, the population keeps multiplying. So, will there be enough energy to go around? Will there be a day that there will not be energy anymore to meet all the requirements and energy needs of humans and of our art and our environment? Can our planet survive infinite energy consumption? Because the way things are going, the way modernization and development is going, we are tilting towards a time, a situation where there will be infinite consumption of energy. The amount of energy we consume will have no limit because of the new technologies that are coming up in the world today. Can this planet survive it? And even if the planet can produce that energy, can it survive producing that energy on a consistent basis? These are questions we want to ask ourselves, and these are questions we want to deal with as we continue in this particular teaching. So what is energy? Let's quickly look at some definitions. Energy is defined as the ability to do work. Okay, so when you move, when you lift something, when you push something, that is work. So the ability to be able to do those is what we refer to as having energy or as energy. The ability to produce heat or light falls under the ability to do work, and that is also referred to as energy. Energy lights up your room. Energy gets you to school. Energy lights up our rooms. Energy gets us to school. Energy helps us to cook our pizza and any other thing that we probably cook in our various homes. Energy helps us to play our favorite shows and watch our favorite movies. Energy helps us to do a host of things. Energy helps us to think and to move. Scientifically speaking, a thermodynamic quantity is equivalent to the capacity of a physical system to produce work or heat. Now, there are several ways to look at energy, several ways to understand the concept of energy that has been researched by several scientists. Another way of considering what energy might be is by making use of the Einstein's famous equation, which says E is equal to mc squared, where E is energy in joules, and it is related with the mass. M is the mass, which is measured in kilogram, and then the speed of light, which is measured in meters per second, and that is the C you can see in that equation. When you rewrite this equation, it is given as mass equal to E over C squared. That means the mass is equal to energy divided by the speed. So what we will see is that mass has weight. Mass has weight. This in turn implies that as we transform energy from one system to another or from one form to another, a small amount of mass is also transferred. This amount is actually very small indeed and undetectable in any engineering sized system. Energy comes in various disguises. That simply means there are different forms of energy. The forms of energy we have, or the various disguises of energy that we have, are listed here. We've got the kinetic energy, we've got the potential energy, we've got the thermal energy, we've got the chemical, electric, nuclear, or mass energy. We will look at each of these forms of energy one after the other very briefly, and then we'll move on from there. The kinetic energy. This is a form of energy associated with a mass in motion. So together with potential energy, it is often referred to as mechanical energy. The kinetic energy of a body of mass n is given as half mv squared. So kinetic energy can be written as E kinetic is given mathematically as half mv squared, where m is the mass of a body measured in kilograms, and then v is the speed measured in meters per second. If we have these equations in their standard form as written here, the kinetic energy would automatically be measured in joules. So kinetic energy plus friction gives us thermal energy. Kinetic energy plus generators in power stations gives us electrical energy. And kinetic energy plus potential energy gives us mechanical energy. So you need to look at these three combinations, and I'm going to try to take it again. You need to look at these three combinations and try to understand them and pay attention to them. Kinetic energy plus potential energy gives us mechanical energy. Kinetic energy plus friction turns to thermal energy. And then kinetic energy plus generators in power stations give us electrical energy. Then let's talk about potential energy. This arises from the position of an object. It is the energy of an object based on the position of that particular object. Okay, so it arises from the position of an object within the potential field or the tension in an elastic system, such as a wound spring. Okay, and in that case, it will be referred to as elastic energy. Most commonly, the force field is the gravitational field that surrounds the Earth. The higher we are, the greater the potential energy we have. Potential energy for an object of mass m at the height of h with acceleration due to gravity, which is usually given as 9.8 meters per second squared, is given as E potential, where E potential represents the potential energy, which will be equal to mgh mathematically. M is the mass, g is the gravitational acceleration, and h is the height of the object. Don't forget, the higher we are, the greater the potential energy that we have. That is why when you look at this expression here, at this particular height, which is the highest form, potential energy is highest, which is 100, and kinetic energy is 0% here. So as we begin to move down this hill, you find out that kinetic energy and potential energy become equal. You will have lost some potential energy when you start to move. When you start to move, you would lose some potential energy and gain that potential energy in kinetic energy. So you see that kinetic energy increased and potential energy reduced, because we do know that energy can neither be created nor destroyed. So when you lose potential energy, it is converted to another form. It's not destroyed, it's not lost, it is converted to another form. So you can see we have kinetic energy here has been gained and we lost potential energy. And then again, at the lowest form, our kinetic energy is going to be highest, and then potential energy will be lowest. That is why we can see we have 100 and we have 0 here. And as you begin to move again, the potential energy begins to move when you get to a particular height, and kinetic energy drops. And then, the movement and then this analysis keeps going, and we have to keep understanding it. Now we have the thermal energy. We've talked about the kinetic energy. We've talked about the potential energy. Let's quickly talk about the thermal energy. This is energy associated with vibrations at the molecular or atomic scale. It is often called the internal energy of a system or of a body. As the body is heated, it gains thermal energy and its temperature rises. When the temperature rises, it simply means that the molecules or the atoms of that body that are held or fixed will begin to lose their position, and then they begin to move. It is important, though, to realize that temperature and thermal energy are not the same. They are not equivalent. The amount of matter is important, as is the specific heat capacity of that particular substance. The specific heat capacity, in simple terms, is the amount of energy needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius. And it is given as E equals mc theta, where m is the mass, c is the specific heat capacity, and then theta will be the change in temperature. And of course, the E will be energy in joules. Let's quickly look at chemical energy. This is exchanged whenever chemical bonds are broken or formed. For some reactions, this process will be exothermic. This simply means that thermal energy is released. For other reactions, it will be endothermic. This simply means that a net inflow of energy is required to allow the reaction to proceed. So energy is not released, it is gained when we say we have endothermic reactions. With the context of this course, the most important chemical reactions are those involving the burning of fossil fuels or the burning of fossil fuels to produce mainly carbon dioxide and water. When we say fossil fuels, we are referring to oil, gas, and coal. If we represent the calorific value of fuel with CV, then the burning of fuel of mass M will produce E equal to CVN. And that ETH will be given in joules. The CV will represent the calorific value, while M will represent the mass. And ETH will be given as the energy measured in joules. So different materials have different calorific values. Fuel has its own calorific value. Wood has its own calorific value. Coal, petrol, biogas, hydrogen, different types of substances have various calorific values. The calorific value of a fuel is the amount of heat energy produced on complete combustion of 1 kilogram of fuel, and the calorific value of any fuel is expressed in kilojoules per kilogram. Hydrogen has the highest calorific value among all the fuels that we know. Now let's quickly talk about electrical energy. When a loop of wire is moved through a magnetic field, some of the electrons in the wire are forced to travel along the wire. Thus, the kinetic energy of the moving wire is transferred to the electrons and a current flows. Electrons are not free to move without resistance. So that resistance actually produces heat, which is harnessed to useful effect in electric fires and the filaments of bulbs. The heating effect of an electric current is easy to calculate. For example, if we have a current and the current is represented with I amperes and the wire has a resistance of R ohms, then the heating effect is given as I squared R. And that heating effect is called heat energy measured in joules. That's the amount of heat energy that will be released every second. Then we have what we refer to as nuclear or mass energy. Nuclear reactions produce a net energy gain. Many elements will undergo reactions in which the total energy needed to hold together the final nuclei is less than that required to hold together the original nuclei. The missing energy leaves the reaction either as electromagnetic radiation or in the kinetic energy of the new formed nuclei and subatomic particles. The Einstein equation we looked at the other time, E equal to mc squared. When we look at that equation, we can see that the new nuclei, once slowed, will also weigh less than the original ones. And such reactions can be viewed as a way of converting mass directly into energy. There are three ways in which nuclei can undergo such transformation. The first one is fission, the second is fusion, and then the third is radioactive decay. In fission, which is FISSION, a nucleus can be prompted to split into smaller nuclei by forcing it to absorb an additional neutron. While in fusion, FUSION, a pair of nuclei can be forced together to create new, larger nucleus. In radioactive decay, nuclei spontaneously decay into other nuclei and subatomic particles. In all of these three cases, the total mass of the nuclei at the end of the process will be less than that at the start, implying that energy has been released or converted to another form. We have just talked about forms of energy. Now let's talk about types of energy. There are two types of energy, and these two types of energy are subdivided into other types of energy. We have the primary energy and the secondary energy. What is the difference between primary and secondary energy sources? Primary energy sources, these are energy sources that exist prior to any human-induced modification. Fuels extracted from the ground, such as coal, crude oil, or natural gas, fall under this category. Energy captured from or stored in natural sources, such as solar radiation, wind, biomass, and so on, are also parts of primary energy. While the secondary energy sources are those from the transformation of primary sources. When you transform primary sources to other kinds of energy sources, those sources are referred to as secondary energy sources. Examples of those include the gasoline fuel from crude oil, diesel fuel from crude oil, charcoal from wood, and so on and so forth. All of the energy sources that we use, except geothermal and nuclear energies, are derived initially from solar energy. You can see we have here, you can see we have fossil fuels coming from the sun, and these are coal, crude oil or petroleum, and natural gas. Also, you can see we have renewable energies coming from the sun. We have solar, wind, hydro, and biomass. There are different sessions of teachings that I have made about each of these sources, so you might want to create some time, to check this channel out and find out some of these other discussions on some of the other discussions on these energy sources. For geothermal energy is formed by radioactive nuclei plus residual accretion energy, while nuclear energy is formed from uranium, usually referred to as stardust. So these are the only two energies, geothermal energy and nuclear energy, that are not from the sun directly, but every other energy source that we use are derived from solar energy. So the fossil fuel that we use today include coal, the oil or crude oil or petroleum, and natural gas. They are derived from organisms, primarily ocean plankton, that grew over several hundreds of millions of years, storing the solar energy which reached the Earth's surface. Let's quickly look at how coal was formed. As you can see, we have swamp, which are several hundred millions of years old. So this is swamp of 300 million years ago. Before the dinosaurs, many giant plants died in swamps. And then about 100 million years ago, you can see we have dirt, dead plants. This is water, this is like the ocean, and then you have animals. And then you can see dirt, this is another layer right below the ocean. And then you can see below the dirt, you have dead plants. So over millions of years, the plants were buried under the water and dead. Then again, you can see we have forest here. Here you can see we have rocks and depth. We have a coal right at the bottom here. So heat and pressure turn the dead plants into coal. So what you will find out is that we have plants that died in swamps, and those plants are buried underwater and dead, and then heat and pressure turn the dead plants into coal. And these are processes that are several millions or hundreds of millions years old. How petroleum and natural gas were formed. Okay, for a start here, about 300 to 400 million years ago, you can see we have small organisms in the ocean, and then 50 to 100 million years ago, that's about 200 to 300 million years after this phase, the organisms turn into oil and natural gas. And when that happens, today what we do have is trapped oil, trapped gas that are usually explored and brought to the surface to be used. So tiny sea plants and animals died and were buried on the ocean floor over time. They were covered by layers of sediment and rock. Over millions of years, the remains were buried deeper and deeper, and then keeps going deeper. The enormous heat and pressure turned them into oil and gas. Today, we do drill down through the layers of the sedimentary rock to reach out the rock formations that contain oil and gas deposits. So when we look at the primary energy, we also have what we call the renewable energies. In this case, we can talk about the hydro, we can talk about the biomass and wind. These are directly or indirectly derived from the energy of the sun. Solar energy, though technically not renewable, is normally classified as such because it is effectively inexhaustible. Non-renewable energies are in finite quantities on Earth. That means they are not many on Earth. Like uranium, they come from the dust of stars. they could have been present at the Earth's formation, which is about 4.5 billion years ago, or like fossil fuels such as coals, oil, shale, crude oil, and natural gas, they could have been synthesized several 100 million years ago. Renewable energies are available as long as the earth and the sun exist. So what you will see here is a bed of different sources of energy that we have. You can see we have the solar radiation, we have the sun shining, and from the sun we can see some of the energies that are actually derived from solar energy. We have the wind for the windmills, we've got the solar panels for solar photovoltaics, we've got a tidal power. You can see other power sources such as nuclear power plant and so on and so forth. You will see quite a number of other processes that go on right underneath here to make sure that we have our fossil fuels. So you can see right underneath the bed here, we have uranium ore, we have hot water going down here for geothermal. This is geothermal. You can see we have some aerobic processes, aerobic metabolism that are going on here. We have anaerobic metabolism, we have photosynthesis, we have all of those leading to fossil fuel. Okay, then we have hydroelectric power plant, photosynthesis from wood, and then we have coal also, which is part of fossil fuels too. So mainly you will see that this diagram just shows you different sources of energy, some of which are from the sun and the others not derived from the sun. Energy can be measured in different ways. The basic unit of energy is joule, and that is defined as 1 kilogram meter squared per second squared. The amount of energy required to lift 1 pound object 9 inches, which is 22.9 centimeters, is what we refer to as joule. 1 pound is 0.45 kilogram. 9 inches is equal to 22.9 centimeters. So the amount of energy required to lift these is what we refer to as joule. This is generally a very small quantity of energy compared to the amount of energy we use in daily life. So there is another unit that is widely used in energy domain, and that is kilowatt hour. 1 kilowatt hour is equal to 3.6 times 10 raised to power 6 joules, which is also approximately equal to 3.6 megajoules. For measurements of heat energy, the calorie, usually given as cal, or its multiple, which can be given as kilocal or kilocalorie, is an older unit which is sometimes still used. 1 calorie is given as 4.18 joules. It is the quantity of heat necessary to increase the temperature of 1 gram of water by 1 degree Celsius. The other energy units we have are the British thermal unit, which is the amount of heat necessary to raise 1 pound of water to 1 degree Fahrenheit. British thermal unit is abbreviated as BTU, and 1 BTU is equal to 1055.06 joules. We also have what we refer to as quad. 1 quad or quadrillion will be equal to 10 raised to the power 15 BTU. Then the other unit of energy we have is ton of oil equivalent, usually referred to as TOE. It is another unit that is sometimes employed for very large amount of energy. It is equal to 10 gigacal or 4.1868 times 10 raised to the power 10 joules. The ton of oil equivalent is the amount of energy that would be produced by burning 1 ton of crude oil. It is often used in energy statistics. It is also often used in energy statistics. Ton of oil equivalent provides a means for making rough comparisons of amounts of energy available from different energy sources. There are several energy units that you should be familiar with. We have multiple prefixes, and then we have some conversion between selected units. So you can see we have the prefixes here, and we have the multiplicative factor. Okay, for giga it is 10 raised to the power 9, as we know. For mega it is 10 raised to the power 6. For kilo it is 10 raised to the power 3. For deca it is 10 raised to the power 1. 10 raised to the power 18 is exa. 10 raised to the power 15 is pecta. Okay, and that continues until centimeters, or centi is 10 raised to power minus 2, milli is 10 raised to power minus 3, micro is 10 raised to power minus 6, as you can see here. And these are the symbols used to represent each of these prefixes or each of these factors. Okay, you can see atto is 10 raised to power minus 18. Most of the popular ones that we'll be using for our calculations would include kilo, mega, giga, and then it would also include centi, milli, micro. And once in a while, we'll use a couple of other multiplicative factors. The conversion between selected units that we have here, how do you convert megajoule to kilocal, and then to toll, and then to BTU, and then to kilowatt hours? On this particular line, you will see exactly how you can convert that. 1 megajoule is, of course, equal to 1 megajoule. 1 megajoule is equal to 238.8 kilocal. 1 megajoule is equal to 2.388 times 10 raised to power minus 5 ton of oil equivalent, and then it keeps going and keep going like that. 1 megajoule is equal to 947.8 BTU. 1 megajoule is equal to 0.2778 kilowatt hours. Okay, so you can check each line and then keep checking and see exactly how some of these conversions are made. How do you measure energy compared to how we measure power? Measuring energy is not the same as measuring power. Power includes a time element. Power is the rate at which energy is produced or used over a given period of time. Power is measured in terms of watt, while energy is measured in watt hours or kilowatt hours. 1 watt of power is equal to 1 joule of energy per second. Electrical power plants are usually rated in terms of megawatts or kilowatts, but most times megawatts. This rating tells us how much electric power can be produced by the power plants when they are operating at their peak. A 1000 megawatt power plant is capable of generating maximum of 1000 megawatt of electricity, or it is capable of generating 1 billion watts of power per second. So you can see quite a number of electrical power measurements right here, and then you can see we have watt, kilowatt, megawatt, right down to megawatt hours. These are for energy. Kilowatt hour is for energy, megawatt hour is for energy, but terawatt is power, gigawatt is power. Okay, and then you can see their definitions right here, and then you can see their common usages. You can see we have power, and then you can see their common usages where they are used, and so on and so forth. When you say 1 kilowatt hour, what does it mean? It means the energy of a device which has a power of 1 kilowatt working for a period of 1 hour. So 1 kilowatt device which is not functioning does not consume energy. When you have a 1 kilowatt device that is not functioning, that is not working, such a device cannot be said to be consuming energy, no matter what the situation is. So as an energy analyst, as someone who wants to go into the study of energy, who wants to go into the analysis, policies, and other kinds of fields that are connected to energy, there are some organizations that we should be familiar with. We have the UN, we have the European Union, we have the OECD, we have the BRICS. All of these we're going to talk about as we proceed. And then we have the OECD, which represents Organization for Economic Cooperation and Development. And then we have the BRICS that represents Brazil, Russia, India, China, and South Africa. That's the BRICS. So you should be familiar with the institutions that are under the European Union. You should be familiar with the countries that are under the Organization for Economic Cooperation and Development, OECD. You should also be familiar with the countries that are under United Nations, and then you should also be familiar with countries that under BRICS, which I currently just mentioned. There are just 5 of them. We have Brazil, Russia, India, China, and South Africa. You should also be familiar with the missions of these organizations. What are the missions of the United Nations? What are the responsibilities that has been bestowed on the European Union? What are the missions of the Organization for Economic Cooperation and Development? What's the purpose of these organizations? You should be familiar with some of these things. Let's quickly look at the Organization for Economic Cooperation and Development. Their mission basically is to promote policies that will improve the economic and social well-being of people around the world. They provide a forum in which governments can work together to share experiences and seek solutions to common problems. They work with governments to understand what drives economic, social, and environmental changes. They measure productivity and global flows of trade and investment in various countries and nations of the world. They analyze and compare data to predict what future trends would look like. They set international standards, global standards on a wide range of things, from agriculture to tax and to safety of chemicals and so on and so forth. There are a number of countries under the Organization for Economic Cooperation and Development, and some of those countries are listed here. You should go through them and just be familiar with them. You can see we have Switzerland, Turkey, United Kingdom, United States, Iceland, Ireland, Israel, Italy, Australia, Luxembourg, Mexico, Netherlands, and so on and so forth. Canada is also included, and initially the Greek was originally known as BRIC before South Africa joined them. With the possible exception of it was just BRIC without the S, and that was before South Africa joined them. With the possible exception of Russia, the BRICS members are all developing or newly industrialized countries. But the story is changing now. Some of them are even more developed now than the developed countries that we know. The BRICS are distinguished by their large, fast-growing economies and significant influence on regional and global affairs. There are some definitions that you should be familiar with. You should be able to explain what those terms mean. One of them is total primary production. When we say total primary production, what are we talking about? What does it evaluate? What does this mean? What are the things included in total primary production? What are the fuels included in total primary production? What are the energy sources included in total primary production? When we say total balance of trade, what does that mean? You have to be familiar with what that implies. What does it mean? Total primary production evaluates the quantity of natural energy resources extracted or produced. And these include coal, gas, oil, electricity, heat, and biomass production. Production of hydro, geothermal, nuclear, and wind electricity is considered as primary production. Then when we talk about total balance of trade, it is the difference between the export and imports. The balance of a net exporter appears as a negative value, while the balance of a net importer appears as a positive value. The balance of geographic and geopolitical zones is simply the sum of the trade balance of all the countries within that particular zone. Total energy includes coal, gas, oil, electricity, heat, and biomass. You should know all of those things and be familiar with them. When we say total energy consumption, what are we talking about? Okay, total energy consumption for each energy product is the sum of the primary production, external trade, marine bunkers, and stock variations. When we say marine bunkers, we are referring to fuel used by boats and aircraft for international transport. Then we should also look at energy intensity of gross domestic product, constant purchasing power parities. The energy intensity is calculated by dividing the total energy consumption of a country by its gross domestic product. It measures the total amount of energy necessary to generate 1 unit of gross domestic product. Total energy consumption includes oil, coal, gas, electricity, heat, and biomass. The GDP, which is also known as gross domestic product, is expressed at constant exchange rate and purchasing power parity to remove the impact of inflation and reflect differences in general price levels. And it relates energy consumption to the real level of economic activity. Using the purchasing power parity rates for GDP instead of exchange rates increases the value of GDP in regions with low cost of living and therefore decreases their energy intensities. Don't forget, energy intensity is calculated by dividing the total energy consumption of a country by its GDP. This is a graph showing world total energy consumption by fuel type from 1990 to 2040. You will see right on the vertical column we have the amount of fuel in BTU, quadrillion BTU here. So you can see this is 50 quadrillion BTU, 100 quadrillion BTU, 150 quadrillion BTU. And this is accurate up until 2010. And then from 2010 up to 2040, all we have is just projection. So you can see we have nuclear, total energy consumption, world total energy consumption. For nuclear, the world consumed just about 25 quadrillion BTU in terms of nuclear. The world consumed close to 50, probably maybe 40 quadrillion BTU in terms of renewables. And then in terms of coal, you can see what is consumed globally. In terms of natural gas, you can see what is consumed globally, right? You can see all of those on this particular graph. Okay, so what we will do is we have to find a way to find accurate figures for 2010 up till 2020, that is 10 years. And we have to plot a graph to show the annual total world's total energy consumption by fuel type. So this brings us to the end of this lesson. In case you have learned something in addition to what you already know and you like this video, please give it a thumbs up. If you have not subscribed, please go ahead and subscribe to this channel. Also, I would encourage you to let me know what you think about the world of energy. Can we truly live without energy? Can the world survive without energy? If we continue to use energy the way we use it, can the world actually support the production of enough energy to meet the needs, the global needs of humans? Please, I would like to read what you think about that. Provide the response in the comment section. See you in the next lesson.